So, we talk about a new problem today called retiming. Although it is introduced at this stage of the synthesis, as we look at the problem, you will realize that it is actually a lot more general with respect to its applicability. The context here is that you would like to optimize sequential circuits. Optimizing combinational circuits is something that comes later, but a sequential circuit has a combinational component and a flip flop and register component. And one way of optimizing the sequential circuits is you just minimize the area of the combinational components or delays of the combinational components independently. There are these two aspects, one is an area and the other is the time. How do you define the time of a sequential circuit? Our circuit overall may look like this. There are blocks of combinational logic that are separated by these register stages. This is a fairly generic way of characterizing any sequential circuit. It is not necessarily unidirectional like this, you may have cycles, all of that is fine. Not within the combinational logic, but certainly from here you could have outputs that are feeding back to some other combinational logic. But one can view the overall sequential circuit as separate pieces of combinational logic and partitioned by stages of registers. That is one view. So, if I were to optimize this, what kind of optimization we are talking about? Of course, if it is an area optimization, then we try to just do a logic optimization of all of those combinational pieces separately. That does reduce the total area. There are the registers here translating to a bunch of flip flops there. We can try to reduce the number of the flip flop and that also reduces area. What if I want to optimize timing? What do we mean by timing? There are two kinds of timing that are involved. Execution time can be represented as the product of two things. One is the latency, which is the number of clock cycles times what? Number of states. The total run time of an application would be consisting of two components. One is how many clock cycles it took, other is unit of the clock period. So, of course, it is just total time that we are talking about. So, that is the clock period. Those are the two components that determine the total execution time. Total execution time is not the only timing related metric. You could also have other metrics like throughput. Throughput would be once in how many cycles are you able to put out a new result. So, these are in some ways orthogonal to each other. These are different metrics. One is how much time does the total execution take. Data is given here and you take that much time and that is our execution time, right. So, that is one metric of time. The other metric is if data is streaming in, right. So, then there is a different metric. You may have that much execution time, but when are you able to accept the next piece of data and correspondingly when are you able to produce the next output. So, if this is where the input is given and that is where the output is ready. The simplest system is one where you accept the next input here, right, and you would take that much more time, that much execution time for the next input and so on. But of course, our systems need not be designed in that way. It is possible that that is my execution time, and even though the first one has not completed, I am able to accept the next input, and maybe if I have designed my system in that way, then maybe the next output is produced after a relatively small amount of time. And similarly, the third input could be processed here and so on. So, such a system requires a slightly different metric than merely execution time, which is the processing time for one packet of input data or something. So, that I would characterize as a throughput related metric. Which is at what rate am I able to accept input, or equivalently at what rate am I able to produce my output. Execution time nevertheless is an important metric. So, what determines the execution time in our sequential circuit?
So, just one question.
Yeah.
Would there be a trade-off possible between execution time and throughput for a circuit?
Yeah, that could be. Yeah, certainly there can be a trade-off. Well, it shows up in the design style. There could be an area implication of a higher throughput.
Right.
That you can see that standard way to do it is by doing a pipelined design. A pipeline design means that if there is a combinational circuit that produces that output, you break it at appropriate times. We will see this same problem in more detail right now, but you break it. How do you break it? You put resistors there. Putting resistors increases the area of the circuit. So, there is some implication there that we will study in more detail, how to manage that implication. But execution time is determined by two things. In this picture, what are those two metrics? What determines latency? What determines clock period? What determines latency here in this circuit?
Size of the combinational circuit.
No. Latency, the way we defined in terms of the number of clock cycles, is an integer. It is a number. That number should be clear from this picture. What is that number?
3.
Yeah, just the number of flip-flop stages through which the data is going. Does not matter how wide or narrow each stage is. Right. That is the other metric, which is the clock period. So, what determines the clock period of this circuit?
Maximum delay.
Yeah, I have to somehow look at the delay through each of those combinational stages, and the maximum out of them tells me the rate at which I can clock that circuit. The fastest rate at which I can clock that circuit ought to respect the maximum combinational delay of any path in any of those pieces of combinational logic. Okay, so in this context, let us see what flexibility we may have. Consider a gate level design of this nature. These registers are just an abstraction of 4 different flip flops that are there here. Right? Each bit corresponds to the Q output of a flip flop that we are taking. We are just calling it a register stage, but there are actually 4 flip flops there. Here similarly there are 2. Timing of this circuit is determined by what? For this given circuit anyway, the number of stages is fixed, right. The latency in terms of the number of clock cycles is fixed. Clock period is what would determine the timing, and that clock period would be what, or cycle time is the same thing. We said that we should look for the longest path through any of those combinational stages, and the longest path here is if you were to go through that and then this and then this. Right? That is what makes the required cycle time at least 7 units. There are a few other components like we had pointed out when we analyzed timing for the behavioral synthesis. There is a setup time for that next stage of the flip flop. There is a propagation delay. Those are of course there. We are just ignoring that, knowing that finally I need to adjust these delays that I get by just looking at the combinational logic to those other things that are constant for this treatment. So, they are not explicitly being handled here. Okay, so that is the cycle time. Can I do something about it? Do you see there is some opportunity for improving the total execution time of this circuit. Total execution time, you do not have that much flexibility anyway. We said it is the product of latency and clock period. Latency in terms of number of clock cycles, can I change for this circuit? It's fixed. If I remove one of those registers, say I remove one of these registers, then somehow I am changing the behavior of the circuit, right. So, behavior means what is the input, that is what is visible externally, right, and similarly the output is what is visible externally. Let us assume that this internal what we are doing inside the circuit, that is not visible external. I can do whatever I want within the circuit, but external behavior I do not change. That is my specification for this class of optimizations. So, then what can I do about it? As a first step, of course, I should minimize the respective combinational logic. In every stage I should go ahead, and we have not gone to the logic synthesis stage, but we know what logic minimization involves, and we can not just minimize, but minimize it for delay, which may be a different minimization than minimizing logic for area, right. If running this circuit at the fastest clock is my objective, then I should be optimizing it for delay. Fine, I can do that. Is there such an opportunity in the circuit? We may not have seen the formal way yet of optimizing for timing, but it is not obvious. There is an inverter and an AND gate, and that path, can it be brought down further, can it be reduced, the length of the path? How about if I consider both the stages together? Let us assume that we have the optimized logic. So, the gates I am not going to change, that is optimized gates. Still there may be an opportunity to make the circuit faster, where faster is defined as the total execution time. There may be an opportunity to minimize that logic. Like I said, let us treat that this is the output of a minimized logic. Of course, this is illustrating an orthogonal concept, that is why it is brought up. But one thing you ought to notice, there is an imbalance between the two stages, right. First stage the delay is longer than the second. Could we do something about it?
We can
Move some
borrow,
logic.
but that depends what kind of register methodology we are using.
These are flip flops.
Okay.
This is just flip flops.
Because latches allow you to borrow or feed
Well,
forward.
define what do you mean by borrow? Structurally you could do something about it. Remember, nobody cares what you have inside those two stages. This first stage of register, these we are not supposed to touch, these also we are not supposed to touch. Anything in between we can
The middle register can be
restructure if we want to. Middle register can be
eliminated if we form a direct path from the register 1 to the register output.
We can shift the logic, put the logic.
middle register can be eliminated. Eliminating the middle register changes the behavior of this circuit. You might actually get the result faster, that is a different thing, but it changes the behavior. In what way?
More of an architectural change.
But what is the behavior that it is changing?
Some states will not be there.
Time will be more. So if I
If you change the cycle time might be more, but you have one clock cycle as opposed to 2 clock cycles. That is the reason for eliminating it, right? There is only one clock cycle. Wait, that does change the timing behavior of the circuit in ways that we do not want to. We said that the cycle to cycle behavior of the circuit as viewed by the external components, whoever is watching that output. Earlier, when you made a change here at the input, the output was ready 2 cycles later. That behavior we want to preserve. If I remove the internal register, then you get the output 1 cycle later. Right, that is a different optimization, we could try that out, but that is not the objective. I am changing the IO behavior of that circuit with respect to the clock edge. Okay, so that's let us not change that. For example, it's allowed or not allowed, it's not clear, right? We said in a behavioral synthesis tool that may be allowed actually. You are allowed to put in or subtract, put in a new cycles, new states, or subtract some states. When you get down to the next level, RTL level for instance, you don't play around with, you don't assume that this flexibility is there. Logic level and so on. This flexibility, but some other flexibility may still be there.
We shift the law from logic of stage 1 to stage 2.
We could shift some logic from stage 1 to stage 2 in a way that the external cycle behavior, clock edge behavior does not change, but it changes what? How does it help to move something from?
Value of the register.
Reduces the maximum cycle time of the first stage is the critical one, right, for this. So, the first stage decreases, the second stage it increases, but that does not matter because the bottleneck is in the first stage, right. So, what is actually happening? So, what do I select? Which gate I select for moving possibly to the next stage? Right, this much combination logic is there, but where I place that register is up to me because nobody is able to watch it externally. So, I can do this, I can just move that gate outside, right. This gate can be moved to the second stage. What is the consequence? Now, let us recompute the critical path, how much delay is there in both the stages. This one has increased. So, these are delays, these numbers that I have annotated are delays. So, this has increased from 2 to 5, but this one has decreased from 7 to 4. So, the maximum delay of any combinational logic path in the overall circuit has decreased. Latency has not changed in terms of number of clock cycles, it has not changed, but the clock period which is the fastest rate at which I can clock this circuit has improved. That is what is the classical optimization called retiming of a circuit. Circuit is given to us, let us assume it is optimized for area or whatever other metrics. So, logic is otherwise minimized, right. But I have the ability to shift around. What have I shifted here? These are the location of the flip flops I have shifted. In this case, from here I moved it back. In fact, moved it back means that actually one flip flop became 2 flip flops, right. That is what happened. There are 3 flip flops there in that register stage now. Nevertheless, my timing has improved.
I have a question.
Yeah.
Please.
So now we have 3 input register and 3 output, whereas earlier we had 2. So this will impact our resource constraint also.
This impacts the number of flip flops. Through doing this, you are increasing the number of flip flops. So, gates you are not changing,
Yeah.
but flip flops you are increasing. So, the total area increases as a result of this. That is the trade off. We have always been pointing to a delay versus area trade off. This is one of them.
So,
Yeah.
are we still doing the behavioral synthesis steps, or are we in logic optimization?
We have transitioned to the next stage. So, but what I do want to point out is, even though this illustration is with gates, you could well replace those gates with bigger units, and all of this analysis is still applicable.
So that is why my
In fact, behavioral synthesis tool do this
they have to
at that level, but these are RTL components, not merely gate level components, but RTL components, and they do this. They are expected to do this.
So typical process we follow is after logic synthesis or any stage when we restructure the netlist in some
Yeah.
manner, we go through a logic equivalence checking where
Yeah.
the RTL is compared against the gate level
Right.
circuit for the functionality. I do not know the full details of it, but wouldn't this break the LEC logical equivalence if I move the register this way?
You are changing the logic of the individual combinational
Yes.
blocks, right. Moving the gate means what? You are of course changing the the logic. You can still do the equivalence, but remember that this is what was done, and maybe as far as functional equivalence is concerned, you can consider dropping those registers, the intermediate registers. But awareness has to be there of doing a structure.
The first one and the second one,
Yeah.
would they be said as functionally equivalent when LEC is done?
We have to tamper with the meaning of equivalence. The overall circuit is still functionally equivalent, but it would be a mismatch if we were to compare the individual stages. Equivalently, we can of course consider this as an area optimization. How? The flip flop count is this, right? There are 5 flip flops here, 3 flip flops here, and 1 over here. As a result of any retiming that you do, here it is the other way around. That register here, these 2 flip flops were moved to the output. That is what happened essentially by moving that gate to the previous stage. It is the reverse of what we did earlier, and what do you see? The number of flip flops has reduced because this middle stage has gone from 3 flip flops to 2 flip flops. This is a different optimization, it is an area minimization optimization, but it is compromising on timing. Yeah. So, you could formulate this as a timing optimization or you could formulate this as an area optimization, still retiming, but the targets can be different. But of course, the popularity of this is in the timing context. Area, we can assume that we are optimizing through other means, and as regards number of registers and number of flip flops and so on. Remember, those decisions are involved in many other optimizations too, like the FSM state assignment problem, encoding problem. There also the choice of the sequential area was involved. How many bits do you use for the state register that was used? Okay, that is the problem definition. The problem is that a circuit is given to us and we would like to restructure it by way of choosing the placement of the registers in a way that the maximum delay through any of those stages is minimized, so that our clock can be the fastest. Is that clear as the just the problem statement?
Every problem can be boils down to a graph problem.
This is a favorite tool of synthesis researchers who know only graphs. So, whatever your problem is, I understand it in terms of graphs. There are many more graphs to come, so just hold on. So, where is the intellectual input over here, since solving these graph problems are some other community's business. We are not smart enough to solve those graph coloring or the other problem that embedding problem that we talked about the other day. Here new problems will also come up, but there is some contribution here. That contribution is right there. Modeling of your problem, whatever it is, in terms of a graph. So, the graph is a sort of a simple mathematical formalism. Once you capture it, then you could ask questions on it. Perhaps those questions are questions that have been asked before in a different context. Of course, you can use all of that knowledge. But this tends to be an important, maybe I would say the most important contribution of synthesis and EDA research in general. That is, you see a problem that seems as though it is very electrical in nature. What you want to optimize delay, anyway, what determines delay? It is an equation that has capacitances and so many other terms, but while you could solve that if the circuit were very small, if the circuit is very large, there is the need to model it in terms of some abstraction for which the solution mechanism scales well. The reason for this kind of formalism is that. Actually, as we solve the retiming problem, we will see that we do borrow other mathematical techniques from different domains. Graph is just the initial representation. But we would like to, of course, use all the mathematical tools that are available to solve our electrical problems, and this graph gives a sort of a nice way to capture some of this. Right. The choice is not obvious. If I have represented it in this way, then it, of course, the reason it was represented this way is that the solution becomes clean or nice, or an elegant solution somehow presents itself once you represent something in that way. Right. In fact, this is an unconventional graph, even though structurally it looks like just a graph, I know everything about it. Even within that, it is not obvious. If I have posed this problem to you, the netlist problem, and if I also give you the hint that you can use a graph, that is also not enough hint for you to to first represent the problem and solve it. So once we discuss the solution, it becomes only then obvious why we are choosing this structure. Graph is obvious, netlist looks like a graph, right? If you change the shape of those gates to all circles, then that becomes a graph. So in that sense, it seems as though there is a very natural mapping. Yeah.
This is not a DAG. So
This is not a DAG, the cycles are there. Right, this
we no longer have DAGs.
yeah, we are moving into more complicated graphs. This is not a directed acyclic graph. So retiming is a problem that works if you have cycles too. They are not combinational cycles, they are every cycle is broken by some register, but that's all right. That does not affect this formulation. So all of those other solutions that you had that worked only on DAGs, they don't work on this. Okay, so we build a graph, that's the easy thing to say, but what is there in this graph? Graph fortunately consists of only two kinds of things. One is a node, other is an edge. So node can represent a gate, that is just a change in shape of these guys. That's very easy. What about the flip flops? Yeah, but it is not obvious that it should be done that way. Right, from the picture you can infer that that's what we have done, but why should we do it in this way? Why don't I make the flip flop also a separate node? No. So that's where there is some intelligence in this whole process. Nodes are gates. So edges represent registers. We attach some weights to both nodes and to edges. Why we do it in this way will become clearer when we do the analysis, but these node weights correspond to the gate delays. Remember, even though we are talking about gates and such things, the retiming is a much more general problem. You could have adders there and you could still pose the retiming problem. You could have other kinds of much more complex units, you could have processors there and you can still ask the same problem. Abstraction changes and correspondingly some of the meaning changes, but nevertheless it is good to think in terms of a concrete example like this circuit to understand, because retiming is something that is popularly done certainly at these lower levels of synthesis abstraction. Okay, so these are the delays. Of course, through this process we have abstracted away some things. We have made the assumption that the gate can be characterized by only one delay number. We already saw earlier that that is an approximation, because every path would have a different delay, right. This path has a different delay, that path has a different delay, high to low transition has a different delay, low to high transition has a different delay, standard condition, minimal, max condition, process corners have different delay. So the delay is in general a much more complicated beast, but this is just abstracted out in terms of one number. That number is the max out of all of those path delays. Okay, so that is the node weight. What is the edge weight? First of all, when do we have an edge? When there is a connection that goes from the output of one gate eventually to the input of another gate, possibly through some flip flops, right, through some register stages. That is when I will include an edge. First of all, it is not a fully connected graph, all nodes do not have edges to all other nodes. So certainly these two nodes do not have edges going from one to the other. These two nodes would have, right, these two nodes do not. That does not mean there is not a path from one node to the other, there actually could be a path, eventual path. You come down this way, you go through this, you can reach that other node. If there is a cycle in the graph, you can reach it, but that is not what we are capturing here. The edge here is an immediate connection from output of one gate to input of another gate through some flip flops possibly, okay, but not through other gates. So that is what we have captured here, and that number there is how many flip flops do you cross in going from one to the other. So things like this, C to D, that number is 0 because it is a combinational path, right. You do not go through any flip flops, but most others you are counting how many flip flops you would go through. So, from F you expect edges to A. In fact, there is only one outgoing edge from F to A, with 1 being the edge weight, because you are going through one flip flop. From some others, like from A, you have paths to C and to E and to F with different edge weights, but you have 3 different paths. So, that is why, okay, is there more? C, D, E, F. Okay, actually to D also there is a path, right. So, C and D it is able to reach with one flip flop stage, and E and F it is able to reach with 2 flip flop stages. So, that is my graph construction. Any questions on this? We should be absolutely clear on the way the graph is extracted from the netlist. Okay. There are some definitions here, note them as we make them. Define a path delay between 2 nodes. Okay, so, that path delay is defined as the sum of the propagation delays of all the nodes along the path, including the endpoints. So, if I have a path like this in my graph from x to w, so this path can now consist of multiple nodes along the path. What are the delays? So, these are the delays, and we say that that path delay from Vi to Vj is the sum of the individual delays of the nodes that are encountered along the path, okay, including the first node and the last node. This is independent of how many registers you are going through, that you are going through 1, 2, 3 registers, that is not counted. This is essentially what we are counting here is the combinational delay from the first one to the last one, if there were no registers in between. It is independent.
Path delays
Without considering registers, for good reason, right, because we might want to move those registers, right. If we move those registers, then we need to respect that path delay. So, anyway, this is defined independent of any registers that are occurring in the path. So, this is not technically what is the critical path the way we define when we analyze a combinational logic, but this is just for the purpose of this optimization, that is the path delay. Okay. And to complicate matters a little bit, we also talk about a path weight. That weight is an orthogonal thing, it is the register count along that path. Right. So, for the same path, the weight would be the sum of these numbers, right. How many registers do I cross as I go from one node to the next one. So, that we represent like this, we say the path weight from I to j is the sum of all the edge weights that occur along the path.
It is a representative of the number of registers in
Right.
the output.
Number of registers as you go from output of one to the input of the next. So, this number is defined in a way that is independent of the delays of the nodes that it is encountering. We are only counting flip flops, not counting how long it takes to go from one node to the other. Okay, so, those are definitions. Retiming of a node is defined as follows. We say that an individual node is being retimed in the graph, which is to say that we are moving some registers from the output of a gate towards its input. The direction is just a convention, it also works if you consider it from input to the output, but for this optimization we will consider that a positive value of a retiming number that is associated with a node means that there are some registers that are moved from its output towards the input. Remember, in the process you may be creating more registers, right. As we move the register from output towards the input, we actually created 2 registers, right. But that is considered a retiming value of 1, essentially it is a number, but we say that amount of synchronous delay that is moved past a node, that is the retiming value that is associated with a node. So, that circuit had a graph that looked like this, and a retiming of b equal to 1 means that you take that one and you move it towards the inputs, you get this kind of a graph as a result of retiming of that particular node B with an integer value 1. This could be positive or negative. Negative means that you are moving things from input towards the output, positive means you are moving it from output towards the input. Okay. And what we just defined was for one node. Retiming of the entire graph means essentially you are transforming the graph. In what way? This graph consisted of a set of nodes, a set of edges and a set of weights on the nodes and the edges. What happens as a result of retiming? What kind of transformation it is? Only edge weights are changing. The nodes are not changing, edges are not changing. So, structurally the graph is not changing, but the numbers on the edges are changing because you have associated a retiming value with every individual node. Those values, some of those values can be 0, it means that you are not moving anything past that node, but some of them could be positive or negative, meaning that some registers are flowing across it as a result of a retiming. So, you think of that retiming of a graph as a vector R, where for every node you are associating an integer. For A there is an integer, for B there is an integer, for C there is an integer. So, the retiming of the graph is just represented as a vector of integers, an array of integers, one for every node, that is all. The transformation we can represent like this: for every edge Vi to Vj, right, there is a retiming number Rj, because j is the output node. If there is a retiming number Rj for this, if there is a retiming value Ri for the node Vi, then Wij was my original edge weight from Vi to Vj. The new edge weight is given by the original number plus the number of registers that you are adding to that edge because you move something across Vj. So, some registers were added because of retiming Vj, some registers were subtracted because of retiming Vi. So, the new number would be Wij plus Rj minus Ri, right. I have I to j. This already had some number 8. So, when I do retiming, I associate a number 1 here and maybe a number 2 here. This 2 means 2 more registers are getting added there, we will call them registers. So, flip flops and registers are used interchangeably. One number here means one register got subtracted from that edge. So, what is the retimed value after retiming? What is the new edge weight? It is 8 plus 2 because you added 2 by retiming j, right, minus 1 because you subtracted one register from there. So, that is what this equation is telling us, plus Rj minus I. Right. So, in this example, if I start with this and I use a retiming vector for the whole graph being 0 1 0 for A, B and C, then the implication is that one register is taken from the output of B and that is moved towards this. Right. So, the new edge weight is 1 minus 1 because that one is taken away. So, the edge BC there is plus 0 minus 1, right. C is not being retimed, nothing is coming from C, but B is being retimed, so 1 is being taken out. So, all the edges can thus be recomputed as a result of one retiming vector. This is still only a representation, we are not solving anything yet, but the beauty of this algorithm is that in fact everything is just representation. At the end there is a trivial solution or at least a known solution. Okay, so, this was the implication on individual edge weights as a result of retiming. We have defined those path weights to be the sum of all the edge weights as you go from one node to another node, right. Remember the path weight definition, it was how many registers are you crossing as you go from one to the other, right. So, The path weight then, as a result of retiming, how would that path weight change? That is my path. Okay. And let us assume that I do retiming. The retiming values for A, B, C, D, E are these. For A it is -1, B it is retiming number is associated with a node, right, saying how many registers are moving past it. So, if these are the numbers, then what are the new edge weights first? This one does not change. This is an output, so we do not know what is happening beyond it, but as a result of E, this one does not change. This anyway, there is nothing that is moved past E. This edge weight is influenced by these two retiming numbers, right. So, from the outside nothing is coming, but because D is 1, you are taking one register away towards the input side. So, the new value is 2. Right. So, I can do this whole thing for all the nodes. So, I get some set of retimed register values. The question is, what is the new value for the path weight? The original path weight from A to E was 1 plus 2 plus 2 plus 3, right, it was the sum of these 4. As a result of retiming, what is happening to the path weight? Can I characterize that in a succinct way? Given that I know all the retiming numbers, what is the change in the path weight?
You should include for the retiming number
So first and last will make the difference.
Only first and last will make the difference. Is that clear?
The rest all cancel out.
Yeah, it does not matter. It is like all the intermediate registers, you are just moving from some place in the path to some other place in the path, it still counts as 1, right. Number of registers may be changing, but the number of registers you need to cross are not changing if you just shift them along the path, right. So, the only thing that should influence is the extreme retiming values of that path. That number, this number and this number should influence the path weights. The other number should not influence the path weight. So, that is what we have captured here. The new path weight as a result of the retiming vector R consisting of all the Ri's would be the old path weight plus Rj, where J is this, and minus Ri where I is the first one. Any questions on this? There is no questions. Right. Okay. Continue with our definitions. So far we have defined small w meaning path weight from node I to node j. Okay. So, here is what is defined. Capital Wij is defined for a pair of nodes Vi to Vj. Problem is there may be many paths between two nodes, a pair of nodes you may have multiple paths, that is what is shown here. Each of them has a path weight, right. ABE has a path weight which is 3 plus 1, ACE has a path weight, this would be some F or something. So, there are 3 paths. The capital Wij is the minimum of those path weights. Okay, so, what I have is 4 here, because these two paths ABE and ACE paths have a path weight of 4, the other path has a weight of 6. So, we do not include that, that is the minimum number, the capital Wij, the minimum of all the paths that are there in the graph.
This is like the minimum time required for reaching from A to E.
Yeah, minimum number of registers you need to cross as you go from A to E. Right.
Translate to time.
Translates to time, but ignoring the delays, ignoring the combinational delays, this is we are only counting the clock cycles. Yeah. Okay, so that is my capital Wij. Correspondingly, let me define a capital D. Remember, the small d was the path delay from one node to the other, that was the path delay. Capital D is defined like this. For all the paths that have weight Wij that we just computed, capital Wij, this is the max of all of those path delays. So, there are two paths under consideration in this example, right. One was the ABE and ACE, AFE that we are taking out of consideration for now, but these two paths both have the same capital Wij. So, in that let us count the path delays, this is the combinational delays, right. So, for the ABE path, right, for that path the sum of the delays is 1 plus 3 plus 2, these node weights are being added to give me the path delay, this we already defined actually. So, similarly for that ACE path, the path delay is 1 plus 2 plus 2, that is my 5. Okay. So, if I enumerate these for all those paths for which Wij is what we selected, then the capital Dij is determined as the max value of all of those paths. At least the definition is clear, why it is done in this way is not clear yet, but this is what is the definition. So, these two things we identified, one is the capital Wij, the other is the capital Dij. D is defined in terms of Wij, you have to first get the Wijs before you can get Dij, because here it is the max of those paths that are selected that have 4 for example in this case. That problem is that there may be multiple paths with the same selected path weight W. So, for those paths you take the max of all the path delays. Remember to separate out weight from delay in this discussion, it is important, they refer to different things. Weight refers to the register count and delay here refers to the combinational delays. Okay. Once you have those definitions, as you do retiming, you go from an original set of edge weights to a new set of edge weights. Also from an original set of path weights to a new set of paths. So, the capital Wijs a new set you get, and correspondingly to that another set of Dijs you may be getting, because the Dijs actually the node delays are not changing through this process, retiming is only changing the edge weights, but the Dij is defined in terms of Wijs, therefore, it might actually change. Even though the individual node delays are not changing, the path delays defined in that way will change, because which paths you select are changing. Okay. So, once you do that retiming, there are a couple of things you need to take care of, which is legality. It should be a legal retiming. For a given node, is there a restriction on what the retiming number can be? Just one node. A node has some
greater than the current weight has, otherwise an active number is implicated.
but my question was simpler than that. My question was, is there any constraint on the retiming value for one node? One node may have some inputs and some outputs, right. This is node I, and what constraint does Ri have? Can it be anything?
Actually, the edge weight depends upon the number of registers in between the two
Yeah,
points.
edge weight is capturing the number of registers.
If there is no resistance, then the weight will be 0. So,
I did not go to edges yet, I am just saying given a node, what are the possible values of Ri?
Sir, Ri can be maximum weight of the output nodes that are going from that.
Okay. So, first of all you understand Ri is an integer. We are looking for integral solutions to this. It can be 0, it can be positive, it can be negative. That is pretty much what our limitation is. You may have solutions to the system of equations that we will build with large or small values. There could be interpretations that you come up with, but essentially you are looking for integer values, positive or negative or 0. What constraint would there be on the set of Ri values? All sets of integers are not necessarily legal solutions, they are not legal.
Sum of weights of sum of out edges, weight of out edges.
Not the sum, the minimum
Yeah, remember Ri value of 1 means you take a register from every one of the outgoing edges and you move it to every one of the incoming edges, that is a value of 1. So, anyway, the all combinations of Ri's are not acceptable for the simple reason that at the end you need a valid graph. That graph cannot have negative numbers on the edge weights. The Ri's can have negative numbers and the meaning is clear what a negative number means, but the weights, since edge weights, since they represent the number of registers at the end of all this, they have to be 0 or more. So, that is a legality requirement, whatever you do on the Ri's, the new edge weights have to be 0 or more, it can't be negative. Okay, that is the easier requirement, but there is the other interesting requirement that it should be timing feasible. The way you move things around, given a clock cycle, you should not be able to find a path in the graph with all 0 edge weights. 0 edge weights means what? No register, it is a combinational path in the graph. No combinational path should exceed your given clock period. Okay, so, that introduces that clock period as a new input here to our strategy. So, if the clock period is given, then a path delay that is larger than that clock period must be broken by at least one register. This is of course an intuitive requirement, otherwise it is violating the sequential behavior of the circuit. You do not have a properly working sequential circuit. Any path delay larger than phi is essentially captured by that Dij greater than phi
Does it mean like
equation.
if we have, does it mean like after every clock cycle we need resistors?
After every clock,
periods, the clock period is like 1 clock.
outputs of a combinational, where do the outputs of a combinational circuit go? They go to registers. Right. So, that was our original picture. Remember, we considered this whole circuit as combinational blocks separated by stages of registers. So, that is what we are saying, that I should not find any path, any combinational path delay. Remember, as a result of the retiming, I am moving my registers around, which will move those path delays around. I can capture this requirement quantitatively using just this simple condition, which is if there is a Dij greater than phi, Dijs are those, remember the way we define those Dijs is the max of all of those path delays for which the Wij is minimum. If the Wij was a larger number like 2 or 3, then I do not need to optimize that is not a candidate that I need to worry about. But if it is small, like if it is 0 for example, then I need to worry, I need to make sure that this path delay is enough. And what we are saying is the relationship is, as a result of the retiming I get a new set of capital Wij's, right, for every pair, all of that has to be recomputed. Now, if it turns out that Dij is greater than phi, right, phi is my clock period, then I require that the capital Wij is greater than or equal to 1. You see that it captures this informal requirement that if the path delay is greater than phi, then it should be broken by at least one register. That is what we are capturing here.
Can't we have a case where the Wij's are very large, but my Dij's are still within phi or maybe less than phi, I mean maybe very less than phi? Can't we have such a case?
Yeah, that is fine. This does not preclude that. We are saying we are concerned about only those cases where Dij is larger than phi. If it is small, then it is okay. It is not even captured in that condition. So, which means it is an acceptable. Yeah, it is an acceptable condition, and this may require a violation. So, we only check the violation. There is a feasibility check, right? We are saying it is timing feasible if that condition is met. Otherwise, also it may be feasible, but infeasible conditions are captured by this, precisely by this condition. That is what we are saying. Okay, so that example we had where I have zeros here, so that path has a weight 0, this path has a weight 0, this path has a weight 1. So, this is 0 because that is the minimum of the path weights. For those we enumerate the path delays as 1 plus 3 plus 2 is 1 and 5 is 1. So, DAE is 6. So, 1 plus 3 plus 2 is 6. Right. So, 6 that is my number. So, what we are saying is that is 0, that is 6. So, if I had phi equal to 5, then this is an infeasible retiming. If this was the result of some retiming, then that is an infeasible retiming. But if it is some number greater than 6, then it is okay. Of course, if these numbers were greater than 0, some number here was greater than 0, resulting in that W prime itself being greater than 0, then it is all right. Then essentially it is this part of it. You need it to be greater than 1 anyway.
After all retiming, after applying all retiming, the retiming vector,
Right.
all the paths should pass.
Yes, this is I j for every I j.
When my design is not timing clean, then it is possible that out of n paths that are failing between two nodes, I may at least try to fix and tell designer that n out of n, m paths are fixable, n minus m are not fixable. You need to go and change your RTL to do that.
Okay.
But if I drop that in this process, if I am dropping the transformation, the vector, then I will lose that information. I may turn out that it is not at all doable, but which are not doable is not getting highlighted.
Yeah, I mean the reason there is an iteration in the design process, you do a timing analysis and indicate that these are the situations, then you go back, you ask the RTL designer to fix his code rather than you do it yourself. Here you are assuming that that is my circuit and I want to optimize it for timing. This obviously does not incorporate any feedback to be given right away. It is an optimization problem.
All I was saying is, let's say there were 10 vectors possible for retiming,
Yeah.
and of all those 10 vectors, when the algorithm tried, it came out that at least one path was always violating. So it will not apply any change and it will give the original circuit back.
Yes, yes, yes.
So the feedback is not quantified which was the most problematic situation.
Feedback can be quantified. We are not doing it, but that is not hard to give for all of those stages. In fact, those Dij values, they could be the feedback.
What I meant was little more than that. So I can get the worst 1 or 2 or 10 or whatever.
Right.
But if tool can tell that out of 10, 8 are fixable, 2 are not fixable, maybe I need to just give a feedback about the 2, but rest all are still doable.
I think this feedback is a separate analysis really. It is not directly incorporated in a retiming optimization. It is incorporated in an overall timing analysis loop in which you would do that analysis and try to give some intelligent feedback, not just that it violates, but which are the paths that violate and how to correlate it to what you wrote in the code. This is a separate analysis really. Here it is more restricted with respect to what assumptions it is making. Okay. So, that is the feasibility check. So, the feasibility of retiming, we are talking about two things, right. One was a legality check, that is very easy to see. It just needs to be, the new numbers all need to be positive. There is a feasibility check, every one of those paths the condition has to be respected, and feasibility of an entire retiming vector is something that translates to just this. A given retiming is feasible if it is legal, that condition we know, and that retimed graph is feasible from a timing point of view. We already defined those conditions. If those two conditions are met, then that retiming vector is feasible. Does that make sense? It requires a proof that I have not given, but we will not discuss why it is so, but it turns out that if these two relatively simple conditions are met, then you have a feasible retiming of the graph.
As of now, just means that we can apply this transformation on our graph and we will still get a valid graph.
Yeah, right.
It does not guarantees that we get a quicker one or a slower one or anything like that.
No, it does.
No, we have not solved the problem yet. Now I have to select the vector in a way that optimizes the timing. until now this is only a feasibility check. As long as those two conditions are met, you at least have a valid graph. That's all.
We will select those vectors which are feasible,
Right.
and then we'll see which one gives
Right.
a
Yeah.
faster
Yeah.
response.
So after all this, so we are just saying that the retiming vector R is feasible if that's the case. First one is for all ij belongs to E, means for every edge that is there, this edge weight. For every edge now, that new edge weight should be greater than or equal to 0, means that new edge weight was what, anyway that wij prime was the old edge weight plus rj minus ri, right, that is greater than or equal to 0, or if you rewrite it, this is my legality check. The r's I do not have yet, but whatever r's I choose, legality checks means this has to be respected. Okay. Second is timing feasibility. This is, you do this for all edges, right. This you do for all paths, for all ij. If it turns out that the d vi vj, if that is greater than phi, for the phi that is input to us, then I require that the capital wij prime that should be greater than or equal to 1. What was this anyway? That path weight was again this, right. The changes depended on the changes on the extreme r. It does not matter what is there within from ri to rj. This is not just one edge, but any number of edges. The path, new path weight is only a function of the extreme values. That needs to be greater than or equal to 1. If I just rewrite it, ri minus rj is less than or equal to this. That is my timing check. As long as these are valid for my selected ri and rj, then I say that this is okay from a feasibility.
We are left with just one condition for feasibility check, that is ri minus ij should be less than wij minus 1, because we need to ensure both the conditions are met.
Yeah, we need to ensure both are
If
met.
that second one is met, first one will be met always.
Right, but the second one is not always there. Second one is there if this condition is true. Remember, if phi is small, then it is not always there. So let us look at it with an example. So the second one is not always there. If it is there, then that takes over, right. So what you have is a system of linear inequalities, where we, as a result of a retiming, let us say I compute the W and the D matrices. Okay. Now you build a set of linear inequalities where you have up to 2 inequalities for every pair of nodes ij that we identified. This is one condition, this is the other condition, but this shows up only when that is true. Okay. So as a first pre-processing step, here is what you would do. For some pairs you may have only one inequality, for other pairs you may have 2 inequalities, but where you have 2 you can drop one of them. Right. So for these 2 would translate to only 1, these 2 would translate to only 1, the more restrictive condition, right, and these ones would just show up. So this is what I have as my system of inequalities. Then I just need to solve for R1, R2, R3, R4, all the Ri's that I have, right. That is all I need to do. How do I solve it?
So it's a ILP.
How do you solve? Have you solved these kind of systems?
ILP? No, I have not studied ILP.
First of all, so this is of course a class of a linear system of inequalities. Actually, we do have this linear programming class of problems where that problem formulation looks similar, not quite the same, but it is similar, where you have some such thing. These are matrices. A is a matrix, x is a vector, that is what we want to determine, b is a vector that is given to us. There are several known techniques. This is a solved problem of course. There is a popular technique called simplex, which is exponential time in principle, but often works very well in practice. There are other algorithms that are more polynomial time, but this is the general linear programming problem. Our example is not an instance of a general linear programming problem. Why is it not? These are integers. Ri and rj are restricted to be integers. Unfortunately, integer programming version of that same thing, integer linear programming, where you restrict the variables to be integers, is a harder problem. If they are real numbers, then it is an easier problem. This is the space. So the general ILP problem is difficult. nothing new. By now you know what to expect in this course.
Synthesis are NP, huh? All problems.
Yet this is an example of a specific instance of a problem that is not difficult. General ILP problem is difficult. This is not a general ILP problem. Not only are these RIs restricted to be integers, but there is another condition. You look at these set of equations, there is something else. This is a special case of an integer linear programming problem, where these coefficients of the variables of the unknowns are all 1 and minus 1. They are all of the kind Ri minus Rj less than or equal to some constant, right. That is my formalism. There is no getting around this. The way we derive this, these are only the kind of equations, inequalities that we will get. This though can be solved in polynomial time. So, that saves us, even though the general ILP problem, all like our scheduling, allocation, all of those things could be formulated as ILP problems. We did not go through that, but you can easily, as a homework and therefore consequently as an exam question, we could say that the problem, you understand the scheduling problem, you could write an ILP formalism for many of the synthesis problems that we have already seen. It does not make it any easier, it only helps our understanding of what are the variables that are involved, what are the constraints, but the ILP problem is hard. But this specific instance of the ILP problem, where coefficients are all 1 and minus 1, which is to say that I have all of them of this form, Ri minus Rj is less than or equal to something, that can be solved. There is an easy solution to this. I think I do not have enough time to go through this, but we will resume it the next time.